So far in this class we've been talking about motion, and, well, we're going to still talk about motion. This motion we're going to talk about is simple harmonic motion. Simple harmonic motion is just a motion of an object that repeats itself, similar to a circle, except for not in a circle. What makes simple harmonic motion unique in itself is that there's a force that is always causing this object to go towards its equilibrium position. And we've talked about equilibrium position before. It's just kind of the normal resting position of the object. So with simple harmonic motion, there is a force, which we will call a restoring force, that is always trying to push this object back to its equilibrium position. One example of simple harmonic motion is to take a spring, put a mass on it, make the mass displace, let go, and you're going to watch the mass and spring oscillate back and forth forever and ever and ever, as long as there's no energy lost to outside forces. Now, the reason why this makes a really good example of simple harmonic motion because of the restoring force. The restoring force in this case follows Hooke's law, which is the amount of force acting on the spring, which we know is equal to the spring constant times the amount of displacement. Now, if I take my mass, I give it some initial displacement, it will oscillate back and forth, and hopefully it should go pass through the equilibrium position each time. Now, this system right here, obviously there's friction. I can't make friction go away, so eventually this system will slow down. But if there's no energy loss, it will just keep going back and forth over and over again. The key parts to this system right here is that the max displacement we're going to call amplitude. So the whole motion, there's displacement, but at either end, there's what we call the amplitude, the max displacement. And not only that, but when it reaches its equilibrium position, the amount of force acting on the system at that moment is zero. Now, the interesting thing about this motion is that it does repeat itself. We just got done learning about angular motion, which is all about repeating and moving in a circle, and it turns out that those two motions relate really well. To show that simple harmonic motion follows that of a circle, we can use a phonograph or an old school record player. So, we turn it on, spins in a circle. What I've done was I've taken a popsicle stick and I've taped it to the side of the phonograph. Spins around, 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 around. And what you can do is you can take a light source, set it up, and shine it so that it projects a shadow or an image onto a wall. Now you can set up the light fixture just so that the radius of the phonograph equals the max displacement or amplitude of the mass spring system. So if you get that set up and you can watch the stick go around and around and around and around, you'll watch the shadow go back and forth over and over and over again. Now, we are interested in the position of the stick, or which we will call X, position. The cool thing to note is that when X equals the amplitude or greatest displacement, that is when the photograph equals either 0 degrees or 180 degrees. And the position of the phonograph or the stick equals 0, or at the equilibrium position, when the angle equals 90 degrees or 270. Well, if we use those two criteria, we know that the simple harmonic motion follows a cosine graph. So, by using x over a is equal to cosine, we can find the position of a simple harmonic motion is equal to x is equal to amplitude times the cosine of the angle. Now, the angle of the object doesn't do us very well with simple harmonic motion because if it's moving back and forth, there really isn't an angle. But we just learned that the displacement or angular displacement of an object is equal to the angular velocity times time. So if we take the angular velocity times the time, we get the angular position. And that still doesn't help us because finding an angular position of an oscillating object doesn't really help. But we know that the angular velocity of an object is equal to 2 pi times its frequency, which does have something to do with simple harmonic motion. Frequency is how often an object moves in a certain amount of time, how many cycles per time. And so if it's repeating itself, we can relate it in the frequency. That brings us to the equation on your equation sheet. The position of a particle in simple harmonic motion is equal to the amplitude times the cosine of 2 pi times the frequency times the time. So if you know the frequency and time of an object, along with the amplitude, then you can figure out its position at any time. Now let's look at the energy of this system. Let's imagine that we take a spring with some spring constant K. I take some mass with some mass M, and I compress the spring. The spring now has potential energy. And now I know that as long as there's no energy lost to outside forces, this system will have this much amount of energy throughout the whole time. I also know that the system will be at its fastest point when the mass hits its equilibrium position. That is when it's going to have its greatest amount of kinetic energy. So I can take the total potential energy before and equal to the total kinetic energy after. So 1/2 kx squared is equal to 1/2 mv squared. I equal those two together, solve for velocity, and then realize that velocity is just distance over time, not worrying about direction. And then I can solve for time in terms of period, which will give me another equation on your equation sheet. The period of a spring system, mass spring system, is equal to 2 pi times the square root of the mass over the spring constant K. Another example of a simple harmonic motion would be that of a pendulum. Now this is only true if the amplitude is small for a pendulum. If the angle is big or the amplitude is big, then things fall apart and it doesn't necessarily follow simple harmonic motion. So whenever we're dealing with pendulums, assume that the angle is small enough to have simple harmonic motion. Now, it turns out that the formula is very closely related to that of a mass spring system, but instead of the mass, we have length, and instead of the spring constant, we have acceleration due to gravity, or g. But the motion is all very similar to simple harmonic motion. As long as there's no energy lost to outside forces like air friction, or regular friction, or sound, or anything like that, a pendulum will just go and repeat itself over and over and over and over again. Do you hear that? That kind of explains the harmonic part of simple harmonic motion. We're going to get into that a little later. But as you can hear, there's a certain amount of frequency going on to the mass spring system. And with this frequency, you will get sound, noise, which we're going to learn about a little later on. But that's where the harmonic part comes from. It's time for some examples.